Roohif accepted. This is the place. I'm the moderator, and now is the time. The topic is, as Roohif chose, which model does celestial navigation work on?
How do you determine it's a globe and it only works on a globe? Nobody can look at the data and tell you you are living on a globe. How do you determine this data fits a globe? When you look at the data, it totally not fits a globe. They made it fit.
Good morning, good afternoon, good evening. This is why celestial navigation only works on a globe. So the time of this observation was 5:48 and 12 seconds. So we just need to interpolate between 5 a.m. and 6 a.m. And just notice that each hour is not exactly 15 degrees. And that's because of what I said a minute ago, that a 24-hour day is actually slightly more than 360 degrees of rotation, which means that 1 hour is very slightly more than 15 degrees.
So there's not much different. 10 seconds on the hour. Let's check the data. If the stars and the sun and the moon go like 15 degrees an hour, I think you make a fucking mistake.
Okay, so here is my set of observations.
Okay, you took those observations from this location, 31st latitude south and the 15th longitude east. I'm here at July 14 when you took the observations at 5:48 and approximately on the same location. So 15 degrees an hour, you say. Let's move an hour forward. 6:48, same location. I will put those two rows from the observed celestial bodies next to each other, and then we see how much the azimuth changes. An hour globe rotation. 15 degrees an hour, you say? I don't think so. What a moron. We even have retro motions. 61 degrees retro motion in 1 hour. And you know what is the best thing? The next day it's almost on exactly the same spot. Akamar. So it's all different, not uniform. And they're all on the same spot the next day. It looks like a miracle.
We have used the sun as an example, but the apparent motion is common to all celestial bodies.
Each hour is not exactly 15 degrees, and that's because of what I said a minute ago, that a 24-hour day is actually slightly more than 360 degrees of rotation, which means that 1 hour is very slightly more than 15 degrees.
This first row show a nice steady 15 degrees an hour. But that's the computed sun that makes the Earth go round.
The apparent motion of the sun is not uniform. For this reason, it would be difficult to construct a clock capable of keeping this irregular time. Therefore, a mean or imaginary sun is used. This mean sun is assumed to have a uniform rate of motion with respect to the Earth, and that rate of motion is equal to the average rate of the apparent or true sun during a year.
Average rate during a year, not even a day. Oh, by the way, this is a US Navy video, an old one. So you must know these are the observed celestial bodies. Those apps here don't use the virtual sun that goes 15 degrees around. These apps use the ZN, the observed sun's location that people see in the sky. And as you can see, it never goes with 15 degrees an hour. ZN, the real celestial bodies. And these Greenwich hour angle Those are the computed celestial bodies. They go perfectly round. This is the mean sun, the fake sun, the virtual sun, the mean moon, virtual moon. These are the real ones. We observe. Yeah.
We imagine the celestial bodies on the celestial sphere to rotate from east to west. The rate of motion is 1 degree of arc every 4 minutes, or 15 degrees every hour, or 360 degrees every 24 hours. 4 minutes later, it will be 1 degree to the west of the prime celestial meridian. An hour later, it will be 15 degrees to the west, and so on. We have used the sun as an example.
Here, 11 o'clock. On June the 21st, the observed sun have an azimuth of 45.7. And an hour later, at 12 o'clock, it have an azimuth of 1.8. I check different locations. Some do more and some do a little bit less. So this is the jump it makes in an hour. Imagine your equatorial mount have to follow that. That's more than 40 degrees. That's almost 3 hours Earth rotation in an hour. And I found places with 110 degrees jump, like I show in my videos.
But the apparent motion is common to all celestial bodies.
How can some Baltard determine he lives in a globe by looking at the observed celestial bodies? It's impossible on a globe to have a retro motion of 61 azimuth in 1 hour. So that means it travels like 6,000 kilometers an hour in the opposite direction. When you translate azimuth to globe rotation, it was 15 degrees an hour. So this is a 60 degrees an hour in the opposite direction. Here 14, here 4.1. Even your star, you observed it 14.3 in a retro motion. A jump of 91 degrees. Put that next to that 61 degree retro motion. That's a difference in azimuth of like 150 degrees in an hour. I wonder if this blind cartoon figure also measured the speed of the shadow of his tiny stick. Alexandria at noon, where the sun have an azimuth of 176, and then an hour later, oh, that is a 66 degree difference in azimuth. Oh, holy fuck, that's like 6,500 kilometers an hour rotation speed. Wow, this stuff makes me dizzy. I wonder how those sheep fuckers back in the days measure this terrain. 800 kilometers. But it have hills and valleys and you have to cross over water. And back in the days they did it with a rope and some pins in the ground. The 153 meters. It go up and down and you need to cross water a couple of times. Here, 380 meters. 400 meters. This go up and down and up and down. So you need to calculate each tiny hill, big hills, mountains. Because to measure a stretch of land you need a straight line. When you cross a mountain the route gets longer, of course. Hey, you even need a rowing boat. And ropes to climb, and how do you take your donkeys with you? Or your camels? Or you walk around it? And then take off the distance you walked? Get the fuck out of here, it's impossible. Yeah, they cannot measure 800 kilometers. That would be more like 1600 kilometers with this terrain. Here, 19 meters. So from 400 meters to 19 meters. 40 meters again. It goes up and down. How did those sheep fuckers measure this? I call it bullshit. All these celestial bodies are the next day more or less on the same spot, even when they travel backwards in all different speeds. That cannot work on your tiny globe model with the celestial sphere that goes uniformly around. And not on your model. Local sun, stars and moons that pop up locally. And you morons also claim that the lines to the celestial bodies from different locations are always parallel. And while you're saying that, you do celestial navigations and make celestial triangles. And those lines to the celestial bodies in those triangles are never parallel.
With these three factors, you can turn to your HO 249 site reduction tables to find two important factors. First, the computed altitude, called HC, from your assumed position to the celestial body. HC is the altitude you would observe with your sextant if you were actually at your assumed position. When you have HC, you can compute the co-altitude, or zenith distance.
I see three angles to Saturn which are not parallel. Here I place my stickman on the GP, the geographical position, and my stickman on the North Pole. Oh look, those lines are never parallel, of course.
This gives you the linear distance from the GP of the celestial body to your AP. Or, in other words, the radius of the circle of equal altitude from the GP to your AP.
Who can show me those lines are parallel?
If we have a star in this position, then we know that its geographical position, or its subastral point, is here, directly below it. At a certain instant of time, a navigator taking an observation of the star, that is, measuring the angle between the horizon and the star, establishes its altitude from his position on the Earth. Note that an observer on the opposite side of the geographical position of the star will observe the same altitude if he is the same distance from its geographical position. From this view, it is evident that any observer at the same distance from the geographical position of the star would observe the same altitude.
Yeah, that sounds very logic. And he can still see the same star. And those lines are not parallel.
To begin with, there is an axis, simply an extension of the Earth's axis. The points of intersection of the extended axis and the celestial sphere are called the celestial north and south poles. Polaris, or the North Star, is approximately at the celestial North Pole, and the rest of the sphere appears to revolve around it. Every celestial body has a point on the Earth directly below it. This is called the geographic position, or GP, of the celestial body. Sometimes it is called the subpoint. If you were at the geographic position of Polaris, the star would be directly overhead at your zenith, and you would be near the North Pole. Similarly, if you were at the equator and the sun was directly overhead at your zenith, you would be at the sun's GP. This principle applies to any celestial body, the moon, a planet, a star, or the sun. You are at that body's GP when it is directly overhead at your zenith.
Flat Earth destroyed with directions to the sun. Let me destroy a globe. You really try to convince me those lines are parallel. Let me show you they are not.
The navigator assumes a position, AP.
Let me place Stickman under that GP location.
And from this point, he draws a line representing the direction of the geographical position of the body.
Oh, a straight line over a curved surface.
The direction of this line is determined by the azimuth of the body, which is one of the values computed when the astronomical triangle is solved. A line drawn through AP at right angles to this line
There is no right angle to a curved line.
represents a segment of a circle of equal altitude, on which he has assumed himself to be located. For this assumed position, represented by the ship, he computes from the solution of the astronomical triangle what the altitude of the body would have been at the instant at which he made the observation.
So the star is just above Stickman's head. And the ship draw a line to that star. So are those lines parallel? So with celestial navigation we don't make a triangulation. You're just a moron like the rest, and now I get lost. You lost, piece of shit. No parallel lines? Do you have some more bullshit?
So, the refraction correction is the calculated angular difference between the apparent position of the star and the actual position. That is, the difference between the angle at which the light comes into the lens, which is this projected line of sight, and the angle at which you would observe the star if there was no atmosphere, which would be a straight line between the sextant and the star. Okay, now the refractive index of air at the surface varies, but the typical value given is around 1.000280. And if we plug that into our formula and convert it from radians into arc minutes, so for Achenar, we get half an arc minute.
This image is a little bit too exaggerated. Don't you think so, moron? So 0.5 arc minutes is 0.008 degrees. That's not really much, moron. And by the way, did you take account for this 25-foot high swell, which gives you a false horizon? Moron. And when you are with your tiny boat on top of that swell, you should use more dip correction, idiot. But it seems times don't take account for that, and you're nitpicking about 0.08 degree refraction.
For Betelgeuse, we get 2.4 arc minutes, and for Canopus we get 1.2 arc minutes. Now we've made all the necessary corrections.
Fucking amazing, bro, but you're not convinced me. This stuff works on your spinning retard ball.
All we need to do is add them to the measured angles to get our true elevation or true altitude.
So for the star Argonaut, you did like 10 arc minutes correction. That's like 0.17 degrees. Let's see how that look like in a 3D model. All the measurements on the star Argonaut. And this was the result. The bottom blue line was the GP line. The line to the GP of the star. And the top line is the one from the observation. So you did 0.17 degree correction. To what I must say? To that virtual star? No, it not even come close. Those lines should triangulate, according to your science. That's like 10 degrees in a different direction. Maybe you show me I modeled this up wrong. And then we compare your model with my model. Then I show exactly what I did here.
For example, the declination of Polaris is approximately 90 degrees. But its altitude varies depending on your location on Earth.
Oh, again a triangulation. Astronomical triangles are not parallel lines. Yeah, it's not my science. I don't make this fucking shit up. It's your own shit.
The farther you move away from the GP of a body, the smaller the angle of altitude. The closer you come, the larger the angle. You must recognize that the distances of space are so great that light from a celestial body arrives at the Earth in a narrow band of rays that can be considered parallel.
Parallel, and at the same moment we can make astronomical triangles. Get the fuck out of here.
The technique of actually plotting a line of position.
All right, final step, and this part really is the nail in the coffin for Flat Earth.
Piece of shit, I just demolished all your globe shit. And now it's time you're starting to debunk me, you and McToon, and that retard fighter Flat Earth.
The final step is drawing circles of equal altitude. And a circle of equal altitude is simply the set of all points on the surface where the observer would measure that elevation angle to that particular star. And the observer could be at any point on that circle. So in this example on screen, let's say the GP of the star is over Louisiana. We need to find all the points on the surface that are, for example, 1,000 nautical miles away from the GP. The question is, what formula am I going to use?
We just use the coordinate system, idiot.
When plotted on a chart of the world with their geographical positions as a center, they would appear like this. Each circle is distorted on the Mercator chart due to the expansion of the latitude scale.
You hear that from the US Navy? We use the coordinate system to do that, and not a map, a shape of a map. As long as a map has a coordinate system, you can draw up equal altitude. Equal altitude on a globe to Polaris. Equal altitude on a globe. Equal altitude to Polaris. It seems you don't understand equal altitude.
To find your precise position on this circle of equal altitude, on this circle of equal altitude, circle of equal altitude, circle of equal altitude, circle of equal altitude,
It seems your circles of equal altitude work better on what you call a flat Earth map. Circle of equal altitude on the Gleason's map. 10 degrees above the equator, Polaris, have more or less the same altitude for all these locations.
Find your precise position on this circle of equal altitude.
And on your tiny globe shit, they're going straight up. Yeah. How do you feel now, moron? Did I make you look stupid? Retard? Imbecile? You have a pretty big hook nose. I bet you're circumcised also. Piece of shit foreskin muncher. Here. Place on my poster. Place of honor. Piece of shit. Next to your friend. McToon. You don't want to show me your Navy pictures? And you don't want to tell me how you figured out the motion of the Earth? And you want to debate me? The debate is already over. Before it started. Fat fuck. You don't understand that? Fucking piece of shit.
That's all, piece of shit.